Welcome, friends, to another incredible episode of Nerding Out with the Queens of Physics. Just remembered the name of this podcast as I said it. And today, your hosts, Jen Helsby, that's me, and
Brittany Kamai.
We'll edit out that delay. Just kidding, we won't. I don't believe in editing, personally. What are we going to be talking about today, Brittany?
So today we're going to be talking about compact interferometers. So these are itty bitty instruments that are really precise length measurements. And we are going to go on this journey of trying to understand why this really technical paper is of interest to the whole wide world, really. Well, to us and other people in the field of astrophysics and really beyond, because you'll find out. Anyway, that is the thing. We're going to talk about black holes, lasers, things like that.
Yeah, I do think everyone is interested in this topic. I believe Kim Kardashian is a big fan of interferometers. She's actually sent in a question for you, which is, could you tell us what these compact interferometers measure?
Oh, that's fantastic. Yeah, John Legend, who's also one of our big supporters, had a similar question. So I'll get right into that. So I'm going to walk us through a bunch of really deep stuff. So one thing I wanted to point out is there's this really cool resource that comes out by the American Physical Society. And so these are short write-ups about technical research papers. And their intent is to communicate what's happening in not a super technical level. It's not like the weeds of the research paper, but it's like a more accessible space. And so I bring that up because this is how this paper came to my attention. And so compact interferometers are like these little itty bitty ones. And what's really unique about what we're going to show you is how small they are compared to the things we usually use to measure ripples in space-time. So feel free to jump into this article. We'll put the link in the show notes. I don't know how to do that, but I'm pretty sure Jen will know how to do that. Yeah, okay, so here's the context. So we are in an era where we're able to measure ripples in space-time, and those are gravitational waves. And so what gravitational waves are is when any sort of object with a mass comes by, it lengthens and shortens the distance between two things. Like the distance between my hand is, I don't know, a few inches. And when a gravitational wave comes by, it expands and it shortens by a few inches, not because my hands moved, but because of space itself moving. So in order for us to measure that, we use interferometers, predominantly these types of interferometers called Michelson interferometers. Oh, I should actually show you a picture of that. I meant to pull that up. Yeah, so there was this man named Interferometers. So there's this man named Michelson, hence the name of the instrument, who put together this optical layout where you start, oh dear, well, I should have done this before. You start with some noise. Oh, welcome Wikipedia. You're fantastic. We love you. So you start with some light source, and at the time, they didn't have lasers, but what you can do now is start with a laser. So in this bottom left corner, you start with a laser, and then you hit an optic. And in this case, what the optic does is half of it's a mirror, so it's going to reflect stuff, and the other half is like a window, so it transmits. And so when you shoot this laser at it, half of it reflects up to another mirror, the other part transmits and comes to this other mirror on the right side of your screen. And then it reflects off those distant mirrors, and then it comes back, recombines here, and then exits at the detector. And for those of you paying attention, that yes, there are laser light that goes back towards the source. And so in practice, we do have other optics set up to protect the laser. But the most important thing to take away from this is that Michelson interferometers are truly the reason we're able to detect these ripples in space-time. And so over the last few several decades, I don't know, 40, 50 years or so, there's been so much work around building these instruments at really, really large scales to measure when black holes smash into each other or neutron stars smash into each other. And if you want to learn about some cool astrophysics, you should listen to our last podcast where we talked about kilonova, which is something you can study with things that come out of Michelson interferometers. So I point this out because there's different types of interferometers. There are ones that go in like a square called a Sagnac, and there's other orientations, but predominantly in the field of gravitational wave astrophysics, Michelson interferometers are bread and butter. So that's when you hear me reference that, that's what we're talking about.
And so how does this relate to LIGO? Is LIGO one of these?
Great question, Jen. Yes, so LIGO is our main experiment to measure gravitational waves, so the Laser Interferometric Gravitational Wave Observatory. We have 2 detectors in the US, one in Hanford, Washington, and Louisiana Livingston. And we're part of a global network that includes Virgo, which is in Italy, Kagra in Japan, and that are currently operating right now, and we'll have one running in India. And so that intro to what LIGO is that in all these spaces, LIGO, Virgo, Kagra, we have these L-shaped Michelson interferometers, and the distance from this mirror, this beam splitter, which is this center optic, to the distant mirror is 4 kilometers long. So US based people, that's 2 miles to get between where this laser that you shot at a mirror at this beam splitter takes 2 miles before it goes and hits another mirror, and then it comes back. So LIGO is at that length scale. Virgo and Kagra are also similar in this kilometer scale Michelson interferometers. So 2 miles is huge, right? So those are big interferometers. And the ones that we're going to talk about today are these itty bitty tiny ones. And we need them to be this big in order to decipher the weird thing is that when black holes and neutron stars smash into each other, and the frequency they do that at really drives the scale and design of the instrument. And they all happen to be at frequencies that our Earth is moving around. So we built like fancy seismic systems to protect from that. Thank you, Jen. And also, if I'm getting off on like technical detours, just be like, what the hell is that? So anyway, so these are Michelson interferometers. So this write-up basically is like, there's this paper that just came out, and they made these really itty bitty interferometers, and it's really unique because of the frequency range that these little baby interferometers will be able to measure. And so one thing before we get into the paper is that things that happen out in the universe, when the phenomenon happen, they will happen in certain frequencies. So if I took 2 black holes and smashed them into each other, depending on the mass of the black hole, where they will merge will produce a signal in a specific frequency range. So if we have black holes that are 10 times bigger than the mass of the sun, or like the size of the mass of the sun, they are going to merge into each other in a frequency range that detectors on Earth would be able to measure. And so looking at this, we're going to walk through this very complicated plot. On the horizontal scale, at the left corner is the longest wavelengths. Okay, so very long wavelengths, very low frequencies. And then all the way at the extreme other end is very shortest wavelengths and the highest frequencies. And then we're going to start in this right corner because this is where the detectors that are on Earth are sensitive. The ones in the middle are the detectors that will be in space. And then this other one is a detector that we use that's the scale of the Milky Way, from pulsars, which are stars in the Milky Way, to act as our detector. And so the vertical axis is that you go from really, really high sensitivity, which is awesome for measuring your signals, to lower sensitivity when you get higher up this vertical axis. So, so the black lines tell you how sensitive your instrument is, and there's different instruments in these plots. So this nanograv, pulsar timing arrays, these are ones that are your gravitational wave detector is as big as the Milky Way, which is insane. It's not a Michelson interferometer, but we do use interferometric techniques to create this type of detector. This next one is the space-based mission LISA that will be launching hopefully soon, which is 1 million kilometers long, and it's two Michelson interferometers together and makes a giant triangle. And so this will be up in space, and it'll have free-floating gold cubes and 3 separate satellites and lasers shooting between them to be the detectors. And then these detectors on the right corner are all the ground-based ones that are at that kilometer scale, so like a couple miles long. And they're different types of detectors. So the ones in the US are called LIGO. Virgo is the Italian one. Geo is one in Germany. There's many more ground-based detectors not on this plot, but we just picked this for the other information in here. So alone, just the black stuff, the black lines tell you how sensitive your instrument is. And then the colorful stuff is what things in the universe would you be able to measure with that detector. So if you look at the left side, this big pink thing is the biggest black holes. When they smash into each other, you need a detector the scale of the Milky Way to be able to measure them. And so every improvement in their detection techniques enable us to get into a range where we'd be able to measure those.
And so the way to interpret this is, since the nanograv like sensitivity curve is only just intersecting with the big colored box that represents billion solar mass black hole mergers, it's only going to detect the closest or like the most massive merger events, because it's only just going into this region.
I wouldn't say the most massive. I would say that, so for every sensitivity curve, the left side is the where you can measure more massive stuff, and then the right side's the less massive stuff.
Okay.
And then this is the peak sensitivity of the instrument. So if I have this little tiny bit of
stuff that corresponds to 10 to the 8 frequency, and that is set by the mass of the object. Gotcha.
Yep.
Okay.
Yeah, exactly.
And then so what would modulate the strength on top of that? Because like there's a whole line of stuff that we cannot see that's at that same mass scale from nanograv. Is that the distance? Is that the main issue?
I don't know if I fully understand your question.
Okay, so rephrasing, like exactly where your mouse cursor is at the bottom of the sensitivity curve of nanograv 2015, anything that at the same X position, i.e. frequency position, below that, we cannot see with nanograv 2015. Why is that? Is it too far away, or is it something else?
A combination. It could be too far from the detector, but overall the amplitude is just the amplitude of the wave that the source produced is too small of an amplitude for us to measure. So if you think about your source generating some wave height, that it just didn't generate a big enough wave height for us to see. So like you could have ones that are generating some strain at like this sensitivity, like the amplitude would be this big, except we're nowhere near that with our noise curve.
Okay, so that makes sense. So is it the case that you can have two systems, each with, we'll say, precisely equal 1 billion mass black holes that are the same in almost every way, but one is detectable and one is not. I guess like the other things that would matter are like how distant are the two black holes in their inspiral. Like if they're really close, just about to merge, they're probably going to have a higher gravitational wave amplitude than if they're far away. So it's like the distance of the two objects in their orbit as they inspiral. Is that correct? Is one of the potential like reasons why the source amplitude will be different?
I can jump to this other picture that I was going to show.
Oh, nice. Okay. We can also put a pin in this question and go back if you want to finish that plot. Up to you.
Okay, cool. Let's go back to this plot. So yeah, we'll come back to that because that image will kind of give you a sense of what that means.
Nice.
So to walk through this plot is that nanograv would be the instrument we would choose. It's funny thinking about a bunch of pulsars as instruments, but nanograv would be the instrument that we choose to measure this source, because you need something that big. And so like to get the physical picture is that if I have a really, really, really big thing, it has a certain diameter. And if I have a second really, really big thing, it has another diameter. And in order for it to not be one big thing, it needs to be separated by some distance. So the size of the source will set how far away they are from each other, which then also sets what frequency these two things are going around each other. So then that's why the most massive stuff are on this left side of our plot. And then when you come to this middle range of this plot, you're looking at less massive stuff than nanograv when you use an instrument like LISA, and you'll be able to measure different kinds of sources. So LISA is our supermassive black hole detector. So supermassive black holes are the ones that are in the center of the Milky Way, for example. So they're like 1 billion times bigger than our sun. So that is like one of the types of sources you would find in LISA. And you couldn't necessarily find a signature from a supermassive black hole in the ground-based detector for that same sort of like reason of like how big the black holes are, and then how much that frequency, like how low that frequency is, because they have to be further away from each other to be a merging system. So there's sources that will only be seen in LISA that you would never be able to see in LIGO or any of the ground-based detectors. And so a lot of the work that the theoretical astrophysics community contributes is to figure out from our astronomical observations of what exists in the universe to produce a signal, how big would that signal be, by running simulations of these general relativity calculations when I take two objects and smash them together. So what's wild is like, I didn't appreciate this, but for one source, it can take like months to run one of those numerical relativity codes to get the strain curve of the prediction of what it would look like in the detector.
And they say Bitcoin mining's bad for the environment. Just kidding.
Gravitational use.
This is actually important, so there's a difference.
Yeah. So so this plot shows us about like another big source that LISA would explore is that your pairs of objects that are going around each other. We often talk about binaries when we're talking about gravitational waves, but they're not the only ones who make gravitational waves. So a lot of times we'll talk about equal mass binary pairs, like they weigh the same. But what's cool about LISA is that you can have one massive object like the black hole in the Milky Way, and you can have an itty bitty little black hole fall into it, and it'll go around the Milky Way, and we'll be able to measure that gravitational wave signature, which is super amazing because it's testing general relativity in the most extreme environment, is like an inspiral into a supermassive black hole with another black hole. So that's another bread and butter science case for LISA, the space-based instrument. And that's this unequal mass, extremely unequal massed black holes. So it's like, if you were studying the size of like Godzilla versus an ant, like that's the relationship that you're kind of able to explore with LISA because of its sensitivity and the frequency range that signal happens.
Is the
you can also
spiral of white dwarfs also extremely unequal masses? Like, is it an inspiral of a white dwarf onto like a binary that is still main sequence?
Well, like wait, so like the white dwarf binary pair or of white
well
dwarf?
Yeah, I'm wondering. Okay, so I was thinking, okay, it's a pair of white dwarfs that are merging, but then I'm slightly confused why it would only be detectable by LISA. Like a white dwarf is going to be less than 1.4 solar masses, and so I would expect it to be more on the right side in this frequency plot, which is why I was like, okay, maybe it's white dwarfs inspiraling onto a larger main sequence star.
Yeah, the white dwarfs in LISA are actually like really close white dwarfs. Dwarfs. I don't know what the plural is.
Two dwarfs.
Is it dwarves or dwarfs?
I don't know.
Because we have dwarfs on the okay. Yeah, the ones the interesting thing is you end up being sensitive to things far away and nearby. And so for LISA, the white dwarfs are nearby objects, and they're nearby white dwarf pairs in that band, where like the supermassive black holes are further away, but they're still merging in this frequency band. I think the other part of your question. Yeah.
Oh, well, what you're saying makes me think that, okay, the reason why these white dwarf pairs are in this region of the frequency plot is because even if they have the same mass as like a neutron star that's 1.4 solar masses, they're going to be a lot bigger, right? It's like the size of the Earth versus the size of like a city. So it's like 3 orders of magnitude. 1, 2, 3. That's about the difference in frequency here. So this is very hand wavy, but that makes sense to me.
Sounds good to me. One of my dear friends, Katie Breivik, works on white dwarfs, and she would talk about this all the time, and I feel like I should know more, but we should just have her on this podcast talk about white dwarfs and why. She is a fantastic, incredibly talented scientist, so we'll bring her along. And she particularly works in this region because, we have this overlay of these different science cases, right? Like, oh yeah, this is a supermassive black hole. This is the inspiral of white dwarfs. But like, there's also like, when you get the signal from an instrument, it doesn't just tell you right away, like, oh yeah, this one goes to this astrophysics and this goes to the other. You need to peel them away. And so that is something that people who work on LISA are trying to figure out, how do we ensure that we know which sources came from when they can be on top of each other at the same time. So there's a lot of research in how to do that when it comes off of this detector. Okay, so then on to the next part of this plot. And so the reason we're in an era where gravitational wave detection is like a way we explore is because we had black holes that were 10 times, actually 30 times as massive as the sun smash into each other, and our operating detectors on Earth, LIGO, Virgo, were able, was that Virgo? LIGO was able to detect them for the very first detection. And since then, we've had hundreds of detections of massive black holes, neutron stars. That's the kilonova paper we talked about last time. And they all are in this lower frequency range in this plot. Hopefully we'll be able to get to a sensitivity level where we can measure gravitational waves generated from supernova. But this is the kind of work that's constantly this iterative process between how do you improve the sensitivity and what astrophysical sources are going to be contributing. And like supernova are not like a really common occurrence. So it's not like you can build these $1 million projects and be like, maybe one day we'll see a supernova. And so luckily there's a lot of black holes and neutron stars that exist in the universe, and we can measure it. Okay, so that was the introduction to this part. So the question that Jen had about your sources merging into each other is that what you're looking at on this plot is the curve on the purple curve is the space-based instrument, so LISA. The orange is LIGO, and that's the one on the ground. And the first detection of gravitational waves is this black line right here. So this, when two black holes smashed into each other, they came into the band at this like tens of hertz.
And is that still
frequency?
the inspiral, the flat part?
Yeah. So this flat part is them, the two black holes going around each other, inspiraling and losing energy. So every time it's going around each other, it's the same way you take like a potato out of the oven and you lose energy and heat. This binary system is losing energy in gravitational waves, which is then why the spiral is going to higher frequencies. So the thing is getting closer and closer together because it lost some energy. And then it gets to a point where they meet, and it becomes this extreme distortion in space-time, which then ends up being like a bigger wave. So the amplitude of the gravitational wave gets a lot bigger. And so then that's why you'll see this like uptick of that's when they're finally merging into each other. And so the two of them go around, smash into each other, extremely distort space-time, and then they now it's one black hole, and it's like kind of ringing. And that's this whole like ring down part of the detection. So the reason this plot was something that we've talked about a whole lot is that it talks about the relationship between certain objects that you can measure in space-based instruments and what we'd be able to measure in ground-based instruments. And so this peak is like, it now has become one. You can track and go back in time and just understand its inspiral from earlier. So when it was further away, and then it gets closer and closer and closer and closer, and boom. Why that's really important is because being able to measure it in LISA will give you such high resolution on where exactly in the sky this merger is coming from, which is so significant for talking to your electromagnetic follow-ups, so your telescope friends, because currently in LIGO, and this is constantly being iterated, we measure something. So it's like hearing something. You're like, I heard something. And you tell your friends to look, right? And you're just like, it's over there. And they're like, cool, man, over there is really big. You need to reduce the space in the sky we're trying to find the thing you hear. And so when you have a combination between what you can measure in LISA, then LISA will be able to be like, in this very tiny itty bitty part of the sky at this exact time, this is when this is going to merge. So what this plot also shows, so this black line is two black holes that were 30 times the mass of the sun. And then it shows if you have more massive or less massive objects, kind of like where they would merge in the...
Those are the different blue lines.
Yeah. Yeah.
What are all the little hashes around 0.01 hertz?
These things?
Yeah.
I don't remember. I read this paper a long time ago.
Okay, no worries.
They might be more massive objects. Not really sure. I could just make some stuff up, but I'm not going to do this because we're recording it and people will listen to me. Yeah, so this is this very amazingly long introduction about why these mini interferometers are interesting is that we currently have developed so much technology. We've tested it. We've flown something up in space called the LISA Pathfinder to test the technology. This has been a project that's been going on for many, many decades to see how we can have this really precise instrument flying in space. And so there's a very direct path for this to happen for LISA. That's the thing that's happening. We have our ground-based detectors that are operational. We're building the future. This in-between space is something that there are some proposals of instruments that could potentially fly. But there isn't really a lot of, I mean, this may have changed in the last few years. There isn't really robust instrumentation exploring this specific region. I think it kind of has
10 hertz.
Mm-hmm.
Is it purely like technical, or is it also like noise sources in that region?
So if you do it on Earth, then this big, huge wall has to do with the seismic activity and the scale of your instrument. So if you made the thing really big, then you can drive that to lower frequencies. You also have to mitigate more seismic activity. And so then it's this balance of the cost and being able to like suppress that. To like get to these levels, I think it's something like 10 orders of magnitude or 8 orders of magnitude of seismic suppression makes these instruments possible. Just like, oh yeah, the Earth's shaking, we're just gonna like suppress that by like a factor of 1 billion, which is insane. Is that 1 billion? 10 to the 8? Yeah, 10 to the 8. Yeah, billions, whatever. So that's this. And then the other piece is like, what unique science case is in this region right here? Because if we can measure stellar mass black holes and on the ground base, we can get to the supermassive black holes with the space base, then how do we get to what astrophysics questions are we answering in this intermediate space? Turns out it's intermediate massive black holes. So black holes tell you different stories of things that happen in the universe. So stellar mass is about the deaths of stars. Supermassive black holes will tell you about like dynamics of like the larger galaxies, and the intermediate massive black holes help us understand that formation and structure process of how we even got to supermassive black holes. Like, how do you make them? Like, do you literally just eat 1 billion baby black holes and make a supermassive black holes? Was there some sort of merger history of these in between black holes? And so like that's what the role of that intermediate mass black hole study is about. And so it's another plot. We'll just stick to the plot on the right so it's not another confusing thing. You got your space base, you got your ground based, and what this is looking at and is that you have binaries that are 1,000 times, 10,000 times, and 100,000 times bigger than the mass of the sun. So the green is the smaller binaries, and then the 10 to the 4 is the dash one is the, what did I say? 1,000, 10,000, and then the solid ones are the 100,000. And so these are intermediate mass black holes. That's the frequency range or mass range of them at different distances away from Earth. So further back in time in the universe. So some of them, the more massive intermediate mass black holes, will merge in LISA. Some of them might merge in or would merge in the ground based, but there's a frequency range where they would only merge in this in between of the space and the ground based. And so that these are the kinds of sources that would you not fully be able to understand unless you had a detector in this space. So that
nice.
is
Okay, and this plot is cool because it also shows us with increasing distance, the strain, which I guess is related to the amplitude in a linear way, goes down. So that also is one of the explanations for the first plot we saw, where there was this huge range. And so the stuff at the very bottom is very far in distance and it's like out of the volume that, in this case, nanograph 2015 was sensitive to. Nice.
Yes. This is the introduction to why these tiny mini black holes or interferometers are interesting. So I'll spend a little bit of time on this because I'm an instrument nerd. So this really caught my eye because of them. Like, the thing about gravitational wave detection, and really a lot of different things, is it's interferometers on interferometers. And so to improve the interferometry, we end up using different interferometers. So for example, when we want to improve the seismic contributions to the large Michelson interferometer, we have a tiny interferometer on top of part of the main interferometer. Oh my God, like it's a drinking game for how many times I've said the word interferometer. So we use them as really precise sensors that help the main detector. It's a mouthful. The other cool piece about this paper is that the sensitivity range is in that in-between frequency range between LISA and LIGO. This detector is, remember how, like I said, LIGO is like 2 miles long by 2 miles. LISA is like 100 kilometers. So it's like I think it's like 100 Earth diameters next to each other or something insane. This is like 100 centimeters, itty bitty interferometers. The difference is the sensitivity isn't as good, yet it's actually just exploring a range that doesn't have any instruments currently there.
Is
so
there
to give
a
you some
sensitivity
numbers,
plot in this paper? No, okay, that's too bad.
Oh no, yes there is. What the hell am I talking about? Yes, there is.
Oh,
there
okay.
is. Yeah, well, I'll get to that in a second.
Okay.
So to give you some numbers, at 100 hertz for advanced LIGO, the second generation LIGO, you get this 10 to the minus 20 meters per root hertz. And this really weird unit is like the amount of length noise you can measure in a different frequency band. So the RMS noise that's why you have a square root over a unit. But that 10 to the minus 20 is just like all of the engineering and that technical stuff that goes into it gets us this low. This instrument is picometer, 10 to the minus 12. So it's 8 orders of magnitude different. So you can't just use one little centimeter scale interferometer setup to go and do the kinds of measurements we've done with these humongous ones. Yet it does offer a lot of opportunity for when you need a really high precision, a tiny high precision interferometer somewhere. And what's cool about the technology advances that we've done in LIGO in the past, it drives research in other areas of physics, a lot of the improvement to seismometers, the ways people study like atomic physics, all comes from a lot of techniques that we developed in gravitational wave instrumentation.
And 1 picometer is still like much smaller than the like size of a proton. It's like 1,000 the size of a proton. So that's pretty wild.
Yeah, it's tiny. Like you can get to this high precision with an itty bitty thing. So as you read this paper, because every listener is going to go read this really technical thing, they kind of talk about some of the other interferometers that exist. So LISA Pathfinder was a space mission to test LISA technology, and they had an itty bitty interferometer on there, which if you're building and trying to send something up into space, you have to care about the footprint, like how big of a thing like you're sending up into space. Like it's so much money, and NASA and spacecrafts and blah blah blah. So everything that you need to do is as tiny as it possibly can. So that's what they talk about up here. And so like the bread and butter of this whole project is this tabletop, and this is, so these, for scale, this is like a 1/4 inch hole, so like a regular screw fits in it. So it's like that optic right there, so that's a mirror. It's about like this big, like quarter size. So it's not a big setup for this layout.
And how much of the
the
whole like instrument are we seeing in that image? Is that the
that's
whole
just
thing?
like the no, that's just like the very end over here.
Okay.
But what's cool is like in that first image I showed you of a Michelson interferometer, we started with a laser and it split off into an L. And rather than splitting off into an L, they go into these fibers. So like an optical fiber, like it's running around in like your internet or whatever. It's the same sort of like shooting a laser into a fiber instead of just like being in free space. And then it goes from there to this beam splitter. And then half of it goes into this little figures and detector. And the other half, so that the L, so you basically have like 2 interferometers in this. So this is one L-shaped interferometer, goes to the long mirror, and then hits this sensing head, is how you can untangle what this picture is. So you have 2 L-shaped interferometers in here, and each of these sensing heads are on separate blocks. What the most wild thing about this whole thing is the way they got to the high precision was all in the way you control the instrument. So this digital control system and the really like novel techniques they use in this is how you can get to low sensitivity. So said another way, if you just set this thing up and you just measured it out, you're not going to get a picometer sensitivity. You need to go through this feedback loop in a very specific way to do the kind of like modulation that you need to do to reduce the sensitivity. I'm like, I could go into like techno jargon, but I'm like trying to just,
and is that the like the deep frequency modulation technique thing? Okay.
Yep. So that's why you see it a lot through the paper, is this like deep frequency and using different so like a control system is like, okay, if I'm driving my car and I'm like stay between the lines, and then like, I don't know, the road's going crazy, the control system is to say stay between the lines, like, oh, compensate. What we're doing in this kind of control system is like getting the laser to stay like stable, like stay stable. And what's the way you do that is you kind of just add this extra little jitter to it, so you know how to subtract that jitter out to make it stable. What you normally do is you have a separate jitter on the laser that you jitter the laser, and then you do some like feedback process to tell the thing, your steering wheel, to stay stable. But what's cool is that the same jitter that comes out of it, like what you measure of what you ended up driving, is the thing that you end up feeding into the way you steer. So if I see you driving all crazy, I'm actually using your crazy driving to make you drive better. Is effectively what the like deep modulation is. Really hope that's the most effective analogy. the authors of this paper will come and tell me at some point. But like, that's the thing that I was just like, oh my gosh, this is crazy. This is how they did this. So a lot of the paper is talking about how they've done that and how to make sure that there's, while they want to explore the low frequency end, they up convert it to the high frequency end and then down convert it in that process, so you know how sensitive you are in the low frequency. And so
is
when
the
Jen
crazy driver omega M?
So that's the modulation frequency. So it's, yeah. Yeah.
Like,
I think
which one is the jitter?
The omega M.
Okay, great. Okay, that makes sense.
Yeah. So these are the kinds of plots in the gravitational wave world you stare at forever, which you all know by now. And this plot on the right, talk about the left if you want to, but this is that total sensitivity that you have for the instrument that you set up. So the red, so what this tells you is like, okay, if I'm at 10 to minus 1 hertz, I have a sensitivity of, the heck is it? Like 8 times 10 to minus 11. So I would be able to measure anything above here with some decent signal to noise. And so that's how you kind of, what these plots tell you is the floor of like how sensitive your noise floor. So if you had some signal that's over here, you're like, good luck, can't find it, with the red curve. And this is, the red curve is saying like, if they don't use their fancy technique of like using your crazy driving to drive more stable, this is what it would look like across this band. And what's beautiful is the blue curve, which is how far it's pushed down your sensitivity. And orders of magnitude, these factors of 10 are just the thing that we're like, oh my God, about. And you can see like in that 10 to minus 1 band, how many? One, nearly 2
Almost
orders
2,
of magnitude.
yeah.
Which is insane, right? From like this, just this frequency control wizardry to make this happen. And so this is a really, really cool aspect of having an instrument that's so little have this high, this good of sensitivity, high sensitivity, yeah, in these frequency ranges, 10 to minus 1, 10 to the 1, or like 10 hertz, a hertz, 10 hertz and below. So this is really exciting. I've said the word seismic and interferometry a million times, but wanting to have sensors for seismic activity, this offers some really neat potential moving forward with a tiny little instrument. I'm not sure, maybe we can look at this now. I wonder if, yeah,
So that's,
it's this,
it's exactly that
the hard thing,
range.
yeah, it's exactly this frequency range. This y-axis is not a one-to-one mapping onto the one in the plot, so we can't just immediately be like, okay, can we measure intermediate black holes, mass black holes, which would be sick if we could, but if it doesn't account for like the length, that's pretty close. Anyway, I'm not sure, but they do talk about their some of the dominant noise sources, and so what you do when you build your instruments is you're like, what is creating all of these lines? What's making this slope? What's making these peaks? And what they found is that they set up their instrument and they had it just in the lab, and then they found like the air was moving around too much, so they built a box around it, and then they put like some foam in it to reduce the air currents. But even that, the air currents within the box was still producing some of this lower frequency noise. So those are the kinds of things
haven't
that you're
done
like,
it in vacuum.
exactly, that's exactly what they said. They're
really?
like,
Okay.
yeah, it's like if we put it in a vacuum system, get to low pressures, then hopefully a lot of that lower frequency noise will go away, which I think is the next direction of this research.
Oh, nice. Okay. And so ADC noise, that's like from the readout of the electronics. Okay.
Yeah, the digitizer. So when you go from a photon hitting a detector to saying like these are the ones and zeros, that's the ADC noise. Shot noise is from the photons hitting the detector, so the laser itself. And then the amplitude of the laser light, that fluctuates because a laser is produced from a crystal, and we pump a bunch of energy into it, and it creates this population inversion of some electrons that are up at the top part of the crystal effectively. And then when they're like, I don't want to hang out with here anymore, then they down convert, and then that's how we end up getting the laser. But it's
so
a crystal,
as they fall down to lower energies, they emit electrons. They emit photons of a specific wavelength. Okay.
Yeah, and so the change, the thermal variations in the crystal will imprint like fluctuations on the amplitude of the laser that comes out. I'm pretty sure these are diode lasers. So they're not necessarily crystalline lasers. So the diodes will have some like electrical modulation on that ends up looking like laser amplitude modulation.
So could you do better with like a nicer laser like that is used in LIGO? Yeah, okay. So that could cut down the noise further, because it looks like they're hitting the floor. That is the laser noise. Okay.
Yeah.
Nice.
And then the like trade-off is then those lasers are freaking huge. The size of the lasers that are used for LIGO. So then it's like, okay. I mean, like,
the instrument's
definitely
like 99% laser by size. Got it.
Yeah. But the amazing thing is a lot of this is in the digital realm. So it's that no matter that size of laser combo of like what's the hardware, you still be able to improve the precision of your interferometer from using that kind of digital control loop techniques. So I think that's also very cool.
That is cool.
That's what I have to say about this paper and intermediate mass black holes and this frequency range and all the detectors.
I am excited to see what happens when they do it in vacuum and like get some better no offense, like great paper, but get some better lasers. I'm not like shaming them for their laser. I know it's hard out there, and I mean, science.
Like, yeah. And I think like what's really awesome about this is that all the components are off the shelf components, and everything in LIGO is like not everything, but like most of it's like some super duper extremely customized whatever. I think like one of the optics, they're like on the order of like $50,000. I mean, they could, or even more. I don't even know. So it's like
US military prices. That's the price of a toilet in the army.
Yeah. Exactly. So it's like if I, as a like everyday researcher, had a little budget and wanted to have really decent link sensitivity for something else, then I can go to like Thor Labs and all these like predominant suppliers and pick them up and make this instrument. Then that's solid. So I think that's also what this offers.
Okay. Well, I think I just read a comment from one of our fans, Snoop Dogg, who is going to try and detect some intermediate black holes later this evening.
That's right, Snoop. Yeah, Snoop. He's one of our supporters, and hopefully we're looking to build a collaboration on our Center for Astrophysics that Snoop Dogg wants to be a part of. So I know you drop your donations constantly to the Queens of Physics, and so we look forward to building the center together.
For legal reasons, I would just like to note that all references to celebrities have been jokes purely for comedic purposes. So nobody sues.
Yeah, like nobody sues. Snoop Dogg has a talk. Yeah, we're broke. Look us up.
There's nothing for you here.
Unless you want to collaborate and we can support the youths, you know.
Yeah, Snoop Dogg Center
yeah.
for Astrophysics. It could happen, you know. You never know.
Gotta be manifesting these things. John Legend backing it, Kim Kardashian.
Yeah, Kardashian
you know?
Center for Astrophysics. That would really be good for the brand. I'm just saying.
Yep, yeah. You gotta hit all the different dimensions. I mean, Snoop Dogg does that. He like cooks with Martha Stewart, you know. So yeah. As Jen said, these people have never talked to us yet.
Okay, I think we should probably pause it here. Another great episode. We'll leave links to the paper in the show notes below. Thanks everyone for watching.
Aloha.